Hello everyone. I am Sutin Guo. I choose this paper from IEEE, and the topic is formal verification of resource synchronization protocol implementations. A case study in RTEMS. This is the outline. The paper focuses on the formal verification of synchronization protocols implemented in an RTOS. The RTOS is the operating system in embedded system. They propose a contract, the obligation of involved primitives and operations, and apply the deduction verification on the corresponding implementation of protocol in your target OS. They present a framework to formally verify the properties of the synchronization protocol that is implemented in the given OS. They provide two case studies to verify ICTP and NRSP, which is implemented in the official RTNS. In consequence, they discover a long state mismatch and provide the possible solution to resolve the mismatch of the both protocols. The verification methods. The test sufficient input and validate derived output, but there is difficult to design a test case that covering all possible situations, and the error may be caused by the interaction of the OS kernel, hardware-specific code, and the employed hardware or simulation platform, and using the model checking. The system is modeled in a formal language, and the properties are specified in logic formulas. A model checker is then used to automatically check the properties, but the problem is it is difficult to specify the system model, and there is no guarantee this is correct. The model is correct. To overcome that, we talk about the next page, the limitation of the above approach. They use a deductive verification to overcome. The one is the Horus triple and weakest precondition. This is the example of the function called FBSDIV. It is doing the the absolute value of x divided by the absolute value of y, and so the whole triple can formulate as this form. The precondition is y is not equal to 0, because the y is gonna, if you divide by 0, you will get error, so the function will return -1. And the post condition, that is, the result is equal to absolute value of x divided by the absolute value by y, and we can devalue to this. The x, if x is greater and equal to 0, the y could be the y could be greater than 0, less than 0, or equal to 0. If x greater and equal to 0 and y is greater than 0, the result is still the absolute value of x and divided by absolute value by y of y. If y less than 0, the result still the same, but if you making the y equal to 0, then the result value will be -1. The x less than 0 is the same result. If y equal to 0, the result still equal to -1. So in this case, the weakest precondition is the y does not equal to 0. So, and this is the same as the precondition. So the program function will be correct because it is the same as the weakest precondition is same as the precondition. Then we can talk about the second property that is derived by the property 1. The result will always greater than 0 because the two value that is greater than 0, so the divide result will be greater than equal to 0. And the derived process is like this. Still the y, if y equals to 0, then the result will always be -1. It is not the result. It is not fulfill the post condition that results will equal and greater than 0. So the weakest precondition still is the y is not equal to 0. Then we can get the two weakest precondition, and they are both fulfill the precondition. So the program will be right, function will be right. Then we are gonna talk about the function contrast. The function contrast, they will describe the behavior, and the require is mean the precondition. So the behavior error there, this its precondition will be if the y is 0, the y will be 0 is the error precondition, and the post condition is the result will equal to -1 because the behavior div is its precondition will be the non-zero y is not equal to 0. So the post condition is result greater than and equal to 0, and the result will be the absolute divide result, and this means the result will not be disjoint. These two behavior will not to be disjoint and complete, and will be complete. And then if we want to verify function contract, we can use the lemma C and its project WP. They will do the static analysis, and the deductive verification of the source code. And the second is the ghost code. It will enable the use of C code within the annotation. This is very helpful when specifying more complex behavior and will affect the behavior of the original source code under analyze. This is the ghost code. The property is in the annotation. And the final is the memory model. It will map the analyze high-level memory concept of types and pointers to a mathematical representation, and use the ACSL to annotate the memory location and pointers. Many can be abstracted from low-level language concepts, support the compiler's specific expansion, and facilitate automatic analysis. Now this is the framework they are proposed. They gonna verify the protocol control resource, and the other that is underlying the OS function will be assumed correct. Using the deductive program verification to verify the source code of the implementation. Make sure the formal specification of all required properties of the resource synchronization protocol is fulfilled. The implementation under verification can be written in high-level programming language. The analysis should be performed in a modular way. Means the set of conditions for function body should be verified based on its statements. And the code function will be two types, divided in two types. One is the specified by the protocol. That is the function that we need to verify. And if the function that provided by the RTOS, the real-time operating system, this function can be assumed to be correct. The workflow step is like this. First, identify the subset of the target OS source code that represent the protocol implementation. 2. Identify the resource synchronization protocol's properties and the rules, e.g. the request and release of the resource. This is an example. 3. Design specification consisting of whole triples for the behavior of all authorized OS primitives. 4. Design specification consists of whole triples for the protocol implementation based on the formal specification of the protocol. Last, verify the specification of the implementation against the source code with deductive program verification aided by appropriate software. And the proposed framework only needs to authorize the cross-compilation toolchain without building or executing the OS code. But the problem is the source code of the target real-time operating system needs to be pre-processed to resolve the inclusion dependency and gain meta information from macros and customized data types. In order to describe the customized data types in the memory model, it will require the information on the bits. Some header files are architecture dependent. This header may come with a cross-compilation tool chain or be generated during the source configuration. To analyze the implementation in RTEMS, the operating system in the embedded system, a separate source configuration is generated for uniprocessor and multiprocessor configurations, respectively. To avoid compatibility problems, 32-bit PowerPC is chosen as the target architecture for the tool chain, which comes with SMP support in RTEMS and is supported by FreeMaC as well. Then it will verify the ICPP in the RTEMS. This is the function that they need to verify: the sys function and the surrender function, and the cross-selling mutex. The sys function will acquire a variable or a self-lock resource, check, and the set owner will check and inherit resource selling, set resource owner, and set resource owner. The surrender function is release a lock resource. Verified properties for sys in the implementation of ICPP in RTEMS. There are 5 properties. 1. A task requires a resource is granted the resource. 2. After a resource is granted, the task runs on the highest selling priority of all currently held resources. 3. Acquiring a resource fails if the priority selling is lower than the acquiring thread's base priority. 4. The resource may be acquired again by the holding thread before release. The level of self-nested access is checked. 5. Acquiring a lock resource enqueues the thread into the resource priority based waiting queue. Such a request operation can be either successful by obtaining the resource eventually, or fail if the request timed out. And the special case is the behavior where a task there is a special case that the behavior where a task suspends while holding a resource is not considered in the ICPP definition, and it may break its priority properties. To address this, there were the necessary conditions. The request resource must be available, or the resource must already be locked by the current requesting task. Available or be locked by the current requesting task. This three conditions align with the formal property of ICPP. That is acquire a lock resource, enqueue the thread into the resource priority based waiting queue. The request operation can be either successful by obtaining the resource eventually, or failed if the request times out. As a result, the fifth case will be excluded from analysis, making a notion for the core mutates slow function unnecessary. This is a function constraint. The function constraint precondition is the mutex and the executing must be valid, and the memory location must not be overlapped, and the mutex owner must be free or be the current requesting task. The behavior of the successful is the resource is locked by the requesting thread, and the resource ceiling priority is inherited. The predicate priority inherited verify if the later path thread and the priority match those contracts in the thread priority add, and ensure the thread priority is updated based on the priority aggregation. Priority inheritance may not result in a priority rest if the thread is already hosts the resource with a higher ceiling. The set owner function will check the resource ceiling is valid or not. If it is valid, then the thread will inherit the resource priority ceiling and will set the resource owner set as the resource owner. If the resource ceiling is violated due to the thread priority, the operation will fail. The contract for ICP surrender is the precondition is the resource queue has to be empty because the ICP does not allow threads to be in queue and waiting for the shared resource. The thread's dynamic priority after surrendering the resource is either lower than before, and it will be checked by the priority revoked, or remain the same because there is another resource with the same ceiling and it still be held. Verification is today there is two tasks, tau 1 and tau 2, and with pi tau 1 greater than tau 2, and the two resource R1 is used by the tau 1 and tau 2, and R2 is used only by tau 2. The product of R1 is equal to pi of tau 1, and product of tau 2 is equal to pi of tau 2. If tau 2 acquire R1, it inherited its priority ceiling and execute with the promoted dynamic priority inherited one. If it requires the second resource R2, the dynamic priority is higher than product of R2 because product of R2 is equal to pi of R2 tau 2, and the pi of tau 2 is less than pi of tau 1, so the dynamic priority is higher than product of R2, which leads to a denial of the resource access by the implemented sharing check, and the data will happen. To address this problem, They correct this mismatch by using the owner's original priority, not the dynamic one. Verification. In MRSP, still verify two functions, the seize function and the surrender function. And seize function will use the client ownership of if the resource is free. Wait for ownership is if the resource is used on another processor, then it will be performed. Because RSP is a multi-processor system, and REST priority always perform to run at the resource local ceiling. The priority of the original MRSP is that each task tau I is assigned to be a specified processor PM, and critical sessions are executed locally, unless a help mechanism is applied. 2. Each resource R3 has one local priority ceiling for each processor PM, which is defined by the highest priority of every task assigned to PM that requires the resource. The product of R3 PM is equal to the maximum pipe of tau I, which is the tau I is the request R3 on the processor PM. For local resources that are not shared between processors, the ICPP rules are applied. For global resources, the ICPP inheritance mechanism is applied with their local priority ceiling. If the request global resource is not available, the requesting tasks spin wait on their own processor in a FIFO order. Help mechanism. A spin waiting task for accessing to a resource must be able to help the current owner of the resource in case the owner is preempted within the critical session. This is a thresh home node. The thresh home node is mean the scheduler node for its original processor. It will be retrieved as a chain element via several nested function call and then executed and extracted by a macro. The macro is expanded over multiple definitions as is eventually based on a compiler specific offset function, which is not able to be formulated in an ACSL contract or logic function. Instead of tracing the complete call and the macro hierarchy, they declare a global ghost pointer G home node of the type of schedule node to represent the executing thresh home scheduler node in the context of the verification. And the contract for MRSP says the condition is a thread acquiring nested resource always requires them in a non-descending order of priority ceiling. Behavior. The current scheduler node's dynamic priority is tracked against the local ceiling of the request resource. Another precondition is a resource that is additionally acquired while being helped by a waiting thread. The behavior is a thread that has migrated to a origin processor inherit the resource local ceiling stored for its home processor and does not affect the priority of the help thread, as long as the thread still holds the resource it is helped with. It stays in the migrated to processor and runs at a legitimate priority. The surrender function is like this. The NRSP thread waiting is there. It will check if the waiting queue exists or not. If it is not has any waiting queue, it will set the owner to reset to null. If it indeed has a waiting queue, then the first thread will be the succeeding owner. These operations are ensured by the stop contract for the queue surrender function. Thread queue surrender sticky. It will ensure the ownership is passed to the next thread and the affected task priorities are updated. The thread as a new resource owner can be abstracted by the ghost variable GNewOwner. In both cases, the surrender thread loses the inherited priority. The actual transfer to the ownership happens in the counterpart during the waiting thread sys function by the queue function thread enqueue sticky. When the function is called successfully, the calling thread is guaranteed to retrieve the ownership of the queue. Furthermore, the waiting thread is expected to have raised its priority to the resource local priority ceiling as expected, expressed by the announcement of the sys function operation. Therefore, the surrendering thread does not have to take care of priority manipulation for other tasks. NRSP in RTMS require nested resource requests to follow a non-descending order of priority ceiling assumption for verification. A thread requiring nested resource always requires them in a non-descending order of priority ceiling. After applying the ICPP remedy and the introduced assumption, all functions were successfully verified using primacy and WP, adhering to NRSP's original definition. If the ceiling check or priority retrieval implementation change, a notion can be updated and the verification can be re-attempted. Today, the ICPP function and NRSP function will choose the two proof goals. One is QED and the other is ALT ERGL, and the time is like this. Time cost is like this. For ICPP, additional mechanisms include the checking resource priority ceiling check, correctness, validating task operation, unlocked resource, ensuring resource access permission, switching the resource owner state to blocked, self-suspending. For an ISP, a priority ceiling check is extended to run idle tests during test migration for improved nested resource access. Function control challenger. Protocol roles are distributed across subfunctions in RTMS. Cell chains of protocol-specific functions require precondition of leaf function to be satisfied by their callers, and the postcondition of leaf function to be relevant to the root functions. Protocols are not always implemented exactly as specified, requiring adjustment for real-world configuration, like self-lock resource of self-suspending owners. Verification relies on treating ICP invariants as preconditions, allowing protocol conforming subsets to be verified efficiently. Introduce polling ghost variable for lock states like thread, mutex, and NISP queues. Include lock states in preconditions and ensure their correctness in postconditions of locking primitives. The top-level function NISP sys or NISP surrender need assign clause to ensure the no unspecified side effects. The framework can be adapted to other operating systems by illustrating necessary OS alternatives like mutex, queues, and threads, or adapting helper the predicates and logic function to the target OS. Sys and surrender function, along with their properties, can be ported to another system with reasonable effort. Conclusion: we propose using function constraint for specifying intended behavior and applying detective verification to ensure components match formal properties, assuming correct parameters. Module verification framework identify mismatch in RTMS, which are corrected, enabling successful verification of ICP and NISP under one additional assumption. With the success of verifying the protocol, we plan to verify other system software in different RTOS for future work. Thank you, everyone.